Areal expansion. Consider a flat metal plate with width W and length L, so its area A is L times W. The metal has a coefficient of linear expansion alpha. Derive an expression in terms of alpha that gives the change delta A in area for a change delta T in temperature. So we have an initial area given by L times W, final area L plus delta L times W plus delta W. So initial area, A initial, is LW. This is before expansion. Then we have a final area, L plus delta L multiplied with omega plus delta omega, or W plus delta W. And delta L, the increase in the length, will be given by the rule of thermal expansion, coefficient of linear expansion alpha, L delta T, and the change in the width delta W will be equal to alpha initial width W times delta T. This is for one-dimensional expansion. Therefore, the change in the area will be A final minus A initial. A final is L times W, that's the first term, plus second term L times delta W, L times delta W, plus third term delta L times omega, or W, W times delta L, and finally we have delta L delta W, plus delta L delta W, and minus A initial, which is LW. So you can see that these LWs will cancel and we will be left with the following. Delta A is equal to L times delta W, where delta W is alpha W delta T, so we can substitute that here. So this will be L alpha W delta T, which is L times delta W, plus then we have omega times delta L, the second term, W times delta L. Delta L is alpha L delta T, so this will be omega alpha L delta T. The third term is delta L delta omega, so we multiply these two, we obtain alpha square omega L delta T square. So we obtain omega L alpha times delta T square. So we can see that delta A can be written in LW parentheses. So these two terms are the same, so we obtain 2 alpha delta T plus alpha delta T parentheses squared. And this can be written as delta A is equal to LW is the initial area, A initial, alpha times delta T, then we have 2 plus alpha delta T. Now, we know that the coefficient of linear expansion alpha is typically in the range 10 to minus 5 to 10 to minus 6 per degree Celsius, typically, if you look up the values in a table, and therefore alpha times delta T is usually much less than 1, and for a temperature change that is not huge, like 100,000 Kelvin or something, and therefore typically we will have alpha times delta t also much less than 2. Therefore, we can neglect this term. So what do we obtain then? Delta A is approximately 2 alpha times the initial area A delta t. So the coefficient of areal expansion is twice the coefficient of linear expansion, 2 alpha. Okay, so to summarize, we have a flat metal plate with original width W and length L, and it goes through a thermal expansion. The length increases to L plus delta L, width increases to W plus delta W. Knowing that alpha is the coefficient of linear expansion, what is the change in the area for a change in delta T given in terms of alpha? So we have noted the final area is L plus delta L times W plus delta W. Subtract the final area from the initial area to obtain delta A, and wherever we see delta W and delta L, we put the linear expansion rule, alpha L delta T, alpha omega delta T. And when we simplify this, we see that at the end we obtain 2 plus alpha delta T parentheses, A initial alpha delta T. Alpha delta T is typically very small, so we can neglect it. So this leaves us 2. So 2 alpha is the coefficient of areal expansion multiplied by area times delta T is the change in the